Okay, today we're going to be looking at section 6.4, Fundamental Theorem of Algebra. The objectives are as follow. We want to construct polynomials with given zeros. We want to determine zeros of polynomial functions, factor polynomials using the conjugate root theorem, interpret geometric meaning of multiple zeros, solve applications of polynomial equations, and solve polynomial equations. So here is the definition of the fundamental theorem of algebra. If P is a polynomial of degree n is greater than 1, P has at least one zero, and so you will have some kind of equation. It could be f of x, p of x. They will change this letter very often. It must be some variable greater than 1, so at least 1, 0. This says p of x equals 0 has at least one solution. It is important to note that the zero of p of p, and consequently the solution of p of x equals 0 may be a non-real complex number. So it's just telling you that it has at least one zero. So it crosses the x-axis if you were looking at a graph at least one time. We will talk about writing this in linear factors. They kind of go through, some math, proof, algorithm information, but it's really hard to follow with all the letters. But it is, worth noting and at least looking over it. I'm going to break it down in layman terms for you as we do the problems. So here is an important piece of information that I think is good. This caution. It says linear factors do not tell us the following things. So once you factor or find the zeros and write it in linear factors, this theorem does not tell you that the polynomial will have all real zeros. Some of them will be non-real or complex numbers. The theorem does not tell us that a polynomial has n distinct zeros, which means n different zeros. Some or all of the constants c may be identical. So sometimes those zeros will repeat. You will have the same one over and over again, which we'll talk about when we discuss multiplicity. And then it says the theorem does not tell us that any polynomial can be written as the product of linear factors. It does not tell us how to determine the linear factors. So all of that is very important. All right, so here I would also note you might be asked to tell the number of turning points. So once you have a polynomial and you look at the largest exponent n, whatever its degree is, you will do n minus 1, and that's how many turning points your polynomial will have. So the number of turning points is your degree minus 1. So in this telling you right here, nth degree of a polynomial has at most n x-intercepts, so it tells you how many times it will cross the line at the most, and then at most n minus 1 turning points. So here's an example. This is a 4th degree. So it says that this polynomial could cross the x-axis at the most 4 times. You can see this one crosses twice. And then it says at the most 3 turning points. So it's going down. This kind of counts as a turn. So there's 1, that's 2, and then 3. So that number of turning points matches up. So multiplicity of a polynomial or a zero is the exponent on that linear term. So right here we have x minus 3. It has a multiplicity of 1. It doesn't have an exponent, so it's understood to be a 1. For this term, which is separated by a comma, it's the same, x minus 3. This one would have a multiplicity of 2, which means that 0 would work twice if you were doing a factoring method. And then here, the multiplicity would be 15. So that's what this is saying. It has a zero of multiplicity K. Now, we also look at the multiplicity to tell us some other information. This will explain whether a graph will cross the x-axis or simply kind of come down here and touch and turn around. So that's what this is telling us. You will have a 0 that crosses the x-axis if the multiplicity is odd. So if we're looking at this like x minus 1 to the third, that's an odd multiplicity. It crosses the line. All right, and then this one says stay on the same side or simply touch the x-axis if it's even. So here we have k plus 2, and that's to the 4th power, and you can see how this kind of comes down and touches the x-axis. It doesn't go across, and then it goes back up. So it just touches. If it's odd, it crosses. If it's even, it touches. So that's what this is saying. And then if it's greater than 1, it will flatten out. So both these examples, you can see how it kind of flattens right here at the x-axis. Even though the odd crosses, it still kind of goes flat for a period of time. And so does this one. So any exponent or multiplicity of greater than 1 will flatten out, odd will cross, and even will touch or stay on the same side. So that will be very important for you to know as well. Then you have some examples provided here, which we will do many of those. And then the conjugate root theorem here, which I will go over, but the main thing is that if you have a complex root, so something with an imaginary part, then so this a plus bi, you will also have a minus bi. So the same term with the minus in the middle. And then we will manipulate those to find real zeros, which I'll just do it as we practice in Hawks. But the conjugate root theorem is just kind of telling you that if you have the positive of it, you're also going to have the negative of it. Here's some examples that they're using with their conjugate root theorem. And then some more examples provided, and that may be it. So they give you a summary. So we're going to be looking at the degree, which tells us how many zeros at max. You can do the degree minus 1 to tell you the number of turning points. We'll try to look at those zeros as linear factors and look at their multiplicity. We will look at whether a graph crosses, touches, or flattens out at the x-axis. And then I think it's pointing us to recall some of the information that we went over in previous sections as far as the rational zero theorem and the Cartesian rule of signs, upper bound, lower bound, and the intermediate value theorem, knowing if we have a 0 between 2 points. So quite a bit of information here, but let's go ahead and jump over into Hawks and start practicing.